The cosmological principle is like a cosmic rule of fairness. It states that on a large enough scale, the universe is both homogeneous and isotropic. But what does that mean? Homogeneity means that if you were to observe the universe from different locations, you'd see pretty much the same thing. Take a look around you. Whether on Earth or in a galaxy far, far away, the distribution of matter is uniform. This idea is foundational for many cosmological models, including the lCDM model. Isotropy, on the other hand, means that the universe looks the same in every direction. No matter which way you look, the laws of physics remain consistent. Imagine you're in the middle of a vast ocean. No matter where you look, the horizon appears the same. These principles are crucial for our understanding of the universe. They suggest that the forces acting across the cosmos are uniform, even though the universe has a foamy texture with galaxy clusters and voids. It still adheres to these principles. Now you might be wondering about exceptions. Sure, there are variations like our sun being different from a black hole or some galaxies moving towards us instead of away. But these variations don't violate the overall uniformity. The cosmological principle relies on the idea that any observer, anywhere in the universe, would come to the same conclusions about its large-scale structure. As Andrew Liddell puts it, the universe looks the same, whoever and wherever you are. The cosmic microwave background provides us with a snapshot of the universe when it was just 380,000 years old. A baby in cosmic terms. This ancient light is remarkably uniform, reinforcing our belief in a homogeneous and isotropic universe. But like any good story, there are some fascinating twists. One of the most significant features of the CMB is something called the dipole anisotropy. Imagine a heat map of the universe with a slight temperature variation. The dipole anisotropy is the largest scale feature in this map and is usually subtracted because of its large amplitude. But why is it there? The standard interpretation is that this dipole is due to the Doppler effect caused by the motion of our solar system relative to the CMB rest frame. In simpler terms, as we move through the cosmos, the CMB appears slightly warmer in the direction we're heading and cooler in the opposite direction. Interestingly, several studies have discovered dipoles in the large-scale distribution of galaxies that align with the CMB dipole direction. However, these dipoles have a larger amplitude than what would be expected from just the CMB dipole velocity. This suggests that something more complex might be at play. A similar phenomenon is observed in radio galaxies, where the amplitude of the dipole varies with the observing frequency. This indicates that these features cannot be purely kinematic. Some authors have even found radio dipoles that align well with the CMB expectations, adding another layer of mystery. Further claims of anisotropy along the CMB dipole axis have been made with respect to the Hubble diagram of type ER supernovae and quasars. Additionally, the CMB dipole direction has emerged as a preferred direction in certain studies of quasar polarizations, strong lensing time delays, and standard candles. Some researchers argue that the correlation of these distant effects with the dipole direction might suggest that its origin is not purely kinematic. Alternatively, data from the Planck satellite has been used to estimate our velocity relative to the CMB independently of the dipole. These measurements, which involve subtle aberrations and distortions caused by relativistic beaming and the Sunyaev-Zeldovich effect, have found a velocity consistent with the dipole, supporting the idea of a kinematic origin. Measurements of galaxy velocities in the local universe show that on smaller scales, galaxies move with the local group, and their average velocity decreases with increasing distance. This observation aligns with the expectation that the CMB dipole is due to the local peculiar velocity field, becoming more homogeneous on larger scales. Surveys have also revealed a low-density region opposite to the CMB dipole, potentially explaining the origin of the local bulk flow. Since the 1990s, observations adhering to the cosmological principle have led scientists to a groundbreaking conclusion. Around 68% of the mass-energy density of the universe is attributed to dark energy. This mysterious force has become a cornerstone of the lCDM model, the prevailing cosmological model that describes the large-scale structure and dynamics of the cosmos. Observations reveal that more distant galaxies are not only closer together, but also contain fewer chemical elements heavier than lithium. Applying the cosmological principle, this indicates that these heavier elements were not forged in the Big Bang. Instead, they were produced through nucleosynthesis in massive stars, which later exploded as supernovae, scattering these elements across the cosmos. Over time, these remnants coalesced into new stars, enriching the universe with heavier elements. Another intriguing observation is that the furthest galaxies, representing an earlier cosmic time, appear more fragmented and irregular compared to their more recent counterparts. This suggests a clear evolution in galaxy structure over billions of years. A related implication of the cosmological principle is that the largest discrete structures in the universe are in mechanical equilibrium. The homogeneity and isotropy of matter at the grandest scales imply that these vast structures are components of a seamless whole, much like the crumbs within a cake. While we can empirically test mechanical equilibrium in surfaces lateral to our line of sight at extreme cosmological distances, detecting this property parallel to the line of sight remains a challenge. Cosmologists agree that a universe adhering to the cosmological principle must be dynamic and ever-changing. In 1923, Alexander Friedmann applied this principle to general relativity, formulating equations that describe the dynamics of a homogeneous isotropic universe. Independently, in 1927, Georges Lemaitre derived equations of an expanding universe from general relativity. Thus, a non-static universe is implied not just by the observation of distant galaxies, but as a natural consequence of applying the cosmological principle to our understanding of general relativity. But what if I told you that recent discoveries have begun to challenge the very foundation of our cosmological understanding? Although the universe is inhomogeneous at smaller scales, the lCDM model suggests it should be isotropic and statistically homogeneous on scales larger than 250 million light-years. However, recent findings, such as the axis of evil, have hinted at violations of the cosmological principle, calling the lCDM model into question. Some researchers now argue that the cosmological principle might be obsolete, suggesting that the Friedmann-Lemaitre-Robertson-Walker metric may break down in the late universe. Several observations have further fueled this debate. The Claus-Camposano Large Quasar Group, discovered in 1991, spans 580 megaparsecs, marginally larger than the expected scale. The Sloan Great Wall, discovered in 2003, stretches 423 megaparsecs, barely consistent with the cosmological principle. More surprising still, U-111, a large quasar group found in 2011, measures 780 megaparsecs, twice the upper limit of the homogeneity scale. Then came the huge LQG in 2012, 3 times longer and twice as wide as our models predicted. And in November 2013, the discovery of the Hercules Corona Borealis Great Wall, a structure measuring between 2,000 and 3,000 megaparsecs, put further doubt on the cosmological principle. In September 2020, a significant 4-9 conflict was identified between the kinematic explanation of the CMB dipole and the dipole measurement in an angular distribution of 1.36 million quasars. The giant arc, discovered in June 2021, spans approximately 1,000 megaparsecs and includes galaxies, galactic clusters, gas and dust. Most recently, in January 2024, the Big Ring was discovered, located 9.2 billion light-years away from Earth with a diameter of 1.3 billion light-years, around the size of 15 full moons as seen from Earth. These colossal structures challenge our understanding of the universe on large scales, suggesting that our models might need significant revisions.